Hello viewers, in today's class we are going to discuss one important problem from integral inequalities. So in this session we'll see how to prove this inequality in which we have the integral 1 to 2 square root of 5 minus x dx is greater than or equal to the integral 1 to 2 square root of x plus 1 dx, right? So in this session we'll see how to prove this inequality by the method of graphs. So let us take this function as f of x and this function as g of x, right? So we'll take f of x as square root of 5 minus x and g of x as square root of x plus 1, right? And we'll graph both the functions on the same rectangular coordinate system. So to graph both the functions, let us take some particular values of x in f of x and g of x, right? So let us take here x and corresponding value of f of x. So let us assign some particular values to f of x. So let us take 0. So f of 0 is square root of 5. Then take 1. This is 5 minus 1 is 4, square root of 4. So we have here 2, right? And then we can take one more value, that is 5. So 5 minus 5, when x is 5, 5 minus 5 is 0, so f of x is 0. And let us take one more value, say minus 4, right? So here we have 5 plus 4, that is 9, so square root of 9 is 3, right? So here we have the table for f of x. Now let us make a table for g of x, and here we have x and here we have g of x, right? So let us take x is equal to 0. So here we have 0 plus 1 1, square root of 1 is 1, right? Now let us take x equal to say 3. 3 plus 1 is 4, square root of 4 is 2, right? And let us take one more value of x. Take x equal to minus 1. So minus 1 plus 1 is 0. So g of x is equal to 0, right? So we have these values, and let us plot these points on this rectangular coordinate system. So let us first take f of x. So here we have x is equal to 0 and square root of 5. The approximate value of square root of 5 is 2.23, right? So when we take x is equal to 0, we have 2.23 somewhere here, right? Okay, then we have 1 comma 2, and here we have 1 and here we have 2, right? And then we have 5 comma 0. So we have we are now taking only 3 points, so we have these 3 points lying on f of x. So the graph of f of x, it goes like this. Here we can write it like this. So we have the graph, that is, it looks like this, right? So here we have the 3 points. This is 5 comma 0, and here we have the point that is 1 comma 2, and here we have the point that is 0 comma square root of 5. So this green curve, it shows f of x is equal to square root of 5 minus x. Now let us plot g of x. So now we have the first point 0 comma 1, right? So 0 comma 1, it lies here, and then we have minus 1 comma 0, and it lies somewhere here, minus 1 comma 0, and then we have 3 comma 2, right? So here we have 3 and here we have 2. So this point, it lies somewhere here, right? Okay, so now we can draw the graph of g of x. So the graph, it goes like this, right? So this is the graph of g of x, that is square root of x plus 1. So now we have the graph of both the functions. So now let us calculate the point of intersection, right? So this is the point of intersection of these two curves, that is the blue curve and the green curve, right? So the point of intersection may be obtained by equating f of x and g of x. So f of x is square root of 5 minus x and g of x is square root of x plus 1. So we have an equation here. So squaring both sides, we have 5 minus x is equal to x plus 1. So this is 2x is equal to 4. So x is equal to 2, right? So here we have x is equal to 2. So this is the point of intersection. When x is 2, the value of the y coordinate may be obtained by f of 2. So this is 5 minus 2, that is square root of 3, right? So the point of intersection of f of x and g of x is 2 comma square root of 3. So this is the point 2 comma square root of 3, right? So this is 2, this is 2 comma square root of 3. So now let us make some observations from this graph, right? Now see here, the limits of integration are from 1 to 2, right? So here we have 1 and here we have 2. So we have to integrate from 1 to 2, right? So this is the first observation, and the second observation is that the green curve, it lies above the blue curve, right? So this is the second observation. The graph of square root of f minus x is lying above the graph of g of x, that is square root of x plus 1, for all values of x that is lying between 1 and 2, because here the limits of integration are from 1 to 2, right? So the graph of square root of f minus x always lies above the graph of square root of x plus 1 in the interval, because we are confined to the limits 1 to 2. So we are talking only about the limits, that is 1 and 2, right? So now from the graph, we see that this function f of x, it lies above this function g of x for all values of x belonging to this interval 1 comma 2, right? So we can say that f of x is greater than or equal to g of x in the interval 1 comma 2, right? So at x is equal to 2, both the functions coincide, right? And for other values of x, the graph of f of x always lie above the graph of g of x in the interval 1 to 2. So now here we apply an important property from definite integrals, right? See, if we have two functions f of x and g of x, as we have here, and the interval is given as 1 comma 2, and in general if we have the interval say a comma b, and f of x and g of x satisfies this property, then the integral from a to b of f of x should be greater than or equal to the integral a to b g of x dx, right? So this is an important property of definite integrals, that is, if f of x and g of x are two functions such that f of x is greater than or equal to g of x in some interval a comma b, then the integral of f of x from a to b should be greater than or equal to the integral of g of x from a to b, right? So here a is 1, b is 2. So now we can substitute the values here. So we have 1, 2, and f of x is the square root of 5 minus x dx, that is greater than or equal to 1 to 2, g of x is square root of x plus 1 dx, right? And that's it. This is the required inequality which is to be proved. So viewers, we can also prove this inequality geometrically by considering the graph of f of x and g of x, right? Now see, we know that the integral a to b f of x dx always represents the area bounded by f of x between these two limits, right? Now see, here we have the integral a to b g of x dx, which also represents the area, right? F of x is square root of 5 minus x, g of x is square root of x plus 1, a is 1 and b is 2, right? So let us consider the area bounded by f of x and g of x in this graph. So now see, here we have this point, right? So let us denote this point by A, this point by say B, this point by C, and this point by D, right? Now since the green curve, it lies above the blue curve, then we can extend this line up to A, right? So now the area bounded by this function f of x from x is equal to 1 to x is equal to 2 is given by a, b, c, d, a, right? So we have the area a, b, c, d, a, and the area bounded by this curve, that is g of x, that is the blue curve, from x is equal to 1 to x is equal to 2 is this area, right? So this area, so here we can take this point as the point say E, right? So the area is E B E B C D E, right? So E B C D E. So the area bounded by g of x dx is given by this shaded region, and the area bounded by this curve f of x from x is equal to 1 to 2 is this additional area including this one, right? So here we have this area also. So we can see from the figure that this area, that is area A, B, C, D, A, is greater than the area E, B, C, D, E, right? And this area represents this integral, which is the integral 1 to 2 square root of 5 minus x dx, and this is greater than or equal to the area represented by this integral, which is the integral 1 to 2, and we have square root of x plus 1 dx, right? So this is how by method of area bounded by curves we can prove these kind of inequalities.